AI is starting to internalize the discovery loop itself, not just predicting answers, but reasoning over structure, testing hypotheses, and improving from its own search traces. That matters because it pushes models beyond static benchmarks into workflows researchers actually care about: biology, chemistry, ecology, optimization, and open-ended science. The common thread here is a shift from generate text to learn how to discover. Keep watching, because the details show how close we are to models that can produce insights you can inspect, validate, and ruse. Let's explore the first paper: Accurate, Interdisciplinary, and Transparent Structure Property, Understanding with Deep Native Structural Reasoning. PsiReasoner, developed by Shanghai Artificial Intelligence Laboratory with Qwen3.14b as its backbone, is a multimodal foundation model that converts protein fold-seq, 3DI, molecular conf-seq, and crystal slices encodings into a unified structure-aware vocabulary so it can reason over structure and text in a single autoregressive trace. The paper's novelty is not just prediction accuracy, but inspectable native structural reasoning. In homology-controlled gene ontology prediction, it lifts low homology cellular component Fmax from 0.42 to 0.55. In single-step retrosynthesis on USPTO 50K, it raises exact match from 0.63 to 0.72. And on DUDE, it preserves the best AUC while improving 5% EF from 7.12 to 7.7. Across the full suite of 86 benchmarks spanning biology, chemistry, and materials, it reports state-of-the-art performance on 67 tasks. The training recipe combines staged, continued pre-training with a self-bootstrapped post-training pipeline that first grounds structural evidence within domains and then consolidates it across domains using RL, which also improves first sample reliability and reasoning quality. Human experts, in a double-blind study against DeepSeek, V4 Pro, preferred or tied PsiReasoner in 98% of comparisons, indicating that its reasoning traces are not only more accurate, but also more auditable and scientifically plausible. Let's explore the second paper: Autonomous Scientific Discovery via Iterative Meta-Reflection. Autonomous scientific discovery via iterative meta-reflection introduces DISCO-PER, a code-driven large language model framework that performs open-ended scientific discovery from raw multimodal data without pre-specified research questions. DISCO-PER uses a generalized propose, evaluate, reflect loop. It generates executable hypotheses, validates each claim with statistical testing on train and held-out splits, and every 5 iterations, a second-order reflection module analyzes the accumulated, accepted, and rejected claims to detect gaps, confounds, and compound hypotheses that steer later search. Evaluated on iNatDisco, a new iNaturalist-based ecological benchmark, the system recovers 8 of 9 literature-backed patterns on iNatDisco, 800, with a 72.7% hypothesis support rate, and 8 of 12 patterns on iNatDisco, 50K, with a 74.2% support rate, outperforming classical causal discovery baselines and guided LLM baselines. The paper also shows that removing reflection drops recall to 7 of 9 on iNatDisco, 800, and 6 of 12 on iNatDisco, 50K, while a counterfactual benchmark confirms DISCO-PER follows the modified data rather than memorized ecological priors. Using Claude Sonnet 4.6, Claude Opus 4.6, GPT 5.4, and DeepSeek V4 Pro, the authors show the method can also exploit images through vision language tools to validate discoveries such as broader mammal geographic ranges and higher latitude fungal niches. Let's explore the third paper: Evolution Fine-Tuning Learning to Discover Across 371 Optimization Tasks. Evolution Fine-Tuning, EFT, developed by researchers at the University of Minnesota, Carnegie Mellon University, KAIST, the University of Cambridge, Hanyang University, and Amazon, reframes evolutionary search as training data, so an LLM can internalize the act of discovery instead of relying on a separate scaffold at test time. The paper builds Finch Collection, a 156,731 trajectory corpus spanning 371 optimization tasks across 10 domains, using OpenEvolve and Qwen 35397b, A17b as the teacher mutation operator, then fine-tunes open source Qwen 3, 5, Qwen 3 models from 2B to 9B parameters. Across 22 held-out tasks, EFT improves the base models by 10.22% on average, with especially large gains on AHC 058 at 290.59% and transaction at 74.3%. And it scales from 15 to 355 training tasks with a 14.1% average held-out gain. On competitive programming, Finch 9B reaches 46.01 average score versus 32.46 for the Quen 3 59B baseline. The method also pairs well with preference learning. KTO on IMP and RED trajectories lifts Finch 8B to 0.3, 81596 on Erdos, and 0.9146 on AC2, and test time RL with Finch matches state-of-the-art on 2 circle packing tasks. Overall, the key novelty is turning long horizon optimization traces into mid-training supervision so small open models can transfer mutation strategies across mathematics, algorithm engineering, GPU kernels, and scientific discovery tasks. That's a wrap on today's AI paper highlights. Thanks for watching.